Okay, so part two, the premise is hot dog eating. So again, the question is, what happens if our sample sizes are not equal? Because when they were equal, it was a pain to calculate the things that we needed, but it was totally plausible. There are three things we have to plug in. I showed you how to calculate that one. You could calculate this one pretty easily as well. It's just not fun. But for looking at, let's look at how terrible it is to compute the F statistic in the case when they're not equal. And this will definitely make you love StatDisk. So our problem statement is, at county fairs around a particular state, there are hot dog eating contests. The people who enter these contests can be categorized as heavy, middle, and light according to their weights. Thus, size will be our treatment or factor, right? The only difference between these people is their size. So at last year's county fairs, a random sample of people from each weight category was selected, and the number of hot dogs eaten by each of the people was recorded. So notice it didn't tell me the size of the random samples, and when I look at the data down here, I can tell they are different sizes. So my question is there a difference between the mean number of hot dogs eaten by these three different sizes of people? Okay, so we would start out with our hypotheses. So in our four-step process, we'd get a little bit more in depth and go ahead and state the parameter and the the statistic. But in this case, we're just going to state our hypotheses. So the null hypothesis would be that each of the means are equal. The mean for the heavy is equal to the mean for the middle people is equal to the mean for the light people. Okay, and then our alternative hypothesis would be that they are not equal. I don't know which one is different or if they're all different, but my alternative is in general just that they are not exactly equal. Okay, so here are their results and their descriptive statistics. I didn't make you calculate them all out by hand this time. The heavy people had a sample size of 4, a mean and variance accordingly. All of that is listed. Okay, so once again, the test statistic F is the variance between samples divided by the variance within samples. But last time we could look at just this in, right? We could plug in the sample size because it was the same for all of them. It worked out. Now they have different sample sizes, right? 4, 6, and 5. Even if one of them has a different sample size, that's a problem. So now we have to take the sum of the sample size for that sample, so it'd be 4 here, times the mean for that sample, minus the mean for all three of them, the grand mean, right? X bar is the mean of all sample means, called the grand mean. I would square those values and then I would add them up. I would do that for each 1, 2, and 3 and then add them up and then divide it by k by minus 1. Remember, k is the number of samples you have. And then I'm going to divide that by this. Okay, I'm just getting tired of actually explaining it. I don't think you really care. I'm not going to go any farther. Basically, this is terrible to calculate by hand. We never calculate this by hand. There's no reason to do that anymore. We use technology. So instead of trying to explain it anymore, let's do it with StatDisk. Okay, so again, our hypotheses are that the mean for the heavy people is equal to the mean for the middle people is equal to the mean for the light people. So our alternative is that the means are not all equal. So we entered the 3 columns of data in the sample editor. So this is what it should look like once you've entered that sample editor. And then we're going to go to analysis and one-way analysis of variance again. So on a different StatDisk site, notice I'm going to go up here to a different one. I've entered those 3 sets of data for the hot dog eating amounts. And now I'm going to go again to analysis and one-way analysis of variance. So again, you'd have to pause this and re-enter your data if you wanted to do this with me. Again, let's see the directions. I think we're on the next page. I'm going to leave my significance level at 0.05 and make sure the boxes are checked that I want that have the data. So 1, 2, and 3 again. So come over here and get 1, 2, and 3, and then I'm going to click evaluate. All right, there's my information. So once I evaluate, I should get this information, and I did. I'm just going to look at it on the paper. So I noticed my test statistic would be 0.53. That's substantially different than last time, right? Substantially smaller. And a smaller test statistic is going to result in a larger p-value. And note, look at this p-value. It's 0.60043. That's huge. There's a 60% chance of getting these sample results purely by chance, assuming the means are equal. So this definitely is not going to reject the null, right? Since our p-value of 0.60043 is definitely greater than alpha, we fail to reject the null. Now, this part is important in being able to interpret. Whenever you fail to reject the null, that means we do not have evidence against the null, and we do not have evidence for the alternative, because against the null and for the alternative are the same. So let's say that we do not have convincing evidence that not all three means are the same, right? Against the null. The null is that all three means are the same. I'm going against it. We do not have evidence against it. Or we could have said that as we do not have convincing evidence for the alternative, so that the three means are different. Okay, so like I said, using StatDisk for these ANOVA problems is so much easier than doing it by hand, but you will not be tested on ANOVA on the final exam. Just wanted you to see that we can extend this to more than 2 populations or more than 2 samples. All right, so that is it for ANOVA. We're going to move on to working through the reviews.